Hello, everybody. Welcome and thank you for attending this webcast. The market briefing from YOL Development and System Plus, dedicated to processor market and technology, CPU, GPU. My name is Faisal El Kamasi. I'm a global support sales and coordination manager for YOL Development. Based on how application processor monitor, the aim of this live market briefing presented by John Lawrence, Technology and Market Analysis at YOL Development, and Belinda Dude, Technology and Cost Analysis at System Plus Consulting, is to provide you in 30 minutes on the recently released processor manufactured with today's leading edge process technology to deliver exceptional performance with a focus on Apple. Before we get started, I remind you that you are encouraged to submit questions to our analysts during all these live events using the Ask a Question windows at the bottom of the screen. Question will be answered right after the presentation. In case we don't have time to answer all of them, we will follow up by email. To conclude, this live event is recorded. You will receive tomorrow an email with the link to the access of the recorded session. So let's start the webcast. Belinda, the floor is yours.
Thank you so much. Thank you everyone for joining us. I am going to be presenting to you the physical characteristics that we have seen in the M1 system on chip. So Apple has actually been using a lot of processors in all their devices, moving from the iPads to the iPhones to the Apple Watch. So here, as you can see, the M1 system on chip is used in the Apple Mac Mini. It's also used in the Apple MacBook Air and the MacBook Pro. This M1 chip, it actually resembles the iPad Pro A12Z. So here, what we have, this chip was actually specifically designed by Apple. It's in-house designed, and it was designed for only their products. So Apple actually outsourced this, it designed and it outsourced the manufacturing to TSMC. The architect and the configuration of this Apple M1 is not totally new. We have the DRAM memory on the side of the M1 component. So here, this is what we have. The M1 chip actually provides a faster CPU performance and also a very fast GPU performance. So with all this performance, we actually have up to 11 trillion operations for each second. So you can imagine the speed on how it works and transfers all this information. Here we have a CT scan. On your right, we have the 3D X-ray image that we can see embedded in the PCB, in this PCB where they actually had to put the Apple and the memory. We actually have the Apple M1 chip. We actually have some embedded capacitors that are inside the PCB. And also we have two DRAM memories that are actually assembled on the same PCB with the M1 chip to actually increase the bandwidth. A teardown is actually performed by my team to actually reveal the M1 chip. Here, our aim was to look at the M1 chip precisely to see the die size. As you can see, the dimensions that we have given you. This is actually a very big die. So here in this die, we had removed the metal cover that was actually protecting the M1 chip, and a thermal interface material is actually deposited on top of the chip in order to help with the heat dissipation. Since this chip is actually a system itself, we actually think that it produces so much heat that needs to be transferred and taken out of the system. Okay, talk about Moore's law. Moore's law has slowed down, but it is not dying. It has not died. Where in 2020, Apple takes out their M1 chip that actually has 16 billion transistors. So they are using a 5 nanometer technology node that allowed them to have up to 16 billion transistors on a single chip. So this number of transistors is very huge. It actually provides supercomputing power and reduced power consumption to all the devices that are actually going to be using this M1 chip. So this is the, oh, it's okay. So here we look at the die blocks. As we said, this is a system on chip. We have different blocks that are actually and different components that are actually integrated on this single die. So what do we have as the main blocks? The three main blocks that we have, we have the core GPU, we have the standard cell logic, these are the transistors, and also we have the HP computing complex. So all these actually make up more than 60% of the die area. So they are taking most of the die area in this functionality chip. As we talk about the tear down that we made, we have an image of the FinFET, as you can see there. So this is actually a new technology. We have so many advantages of using 5 nanometer technology. And also, as you use 5 nanometer technology, this comes down to a new technology that is being made. So there is so much investment that has to be put in to actually to be able to actually produce 5 nanometer FinFET transistors, and you actually have to develop new material that you are going to use for the fabrication. And because most of the manufacturers, they do not have the experience, and they have as this is new manufacturing process, there are lower yields that are going to be expected. In the previous slides, I talked about the die being very huge. So what does this mean in the manufacturing process? The dies, the dies were very huge, and in our estimation, we estimate that there are less than 600 dies per wafer. Here we're talking about a 300 millimeter wafer. So the lower the number of dies on your wafer, this means that there are lower devices or components that you can actually take out from a single wafer. So here with the big die, with the semiconductor manufacturing technology, and the rule is the bigger the die, you are going to have less yield that you're going to have, because just one die, if there is a problem with just one die, you are losing a lot from the wafer. So also we will go to the cost. The cost is high. So this is one due to the new technology that is being done, the investment in the equipment, and sometimes the investment in the new clean rooms that you have to use, and also the new expertise that you have to hire and the people that you have to pay, and also not forgetting the lower yields as you are starting to process this type of technology. So here you also have to concentrate and know the costs that you're looking at when we're talking about the 5 nanometer technology. So finally, what I would want to give you out is Apple has actually entered the processor market by designing their own chip. This is the new processor that has been designed by Apple. So what have Apple gained from this? They have gained a supply chain control. So part of the supply chain has been managed by Apple internally. So this is very good for them. And also we have to think about the 5 nanometer transistors that are providing the high density and the high performance. They come at a cost. The architecture and the technology, it provides the industry with very high performing, fast processing, and power saving processors that can be used in the new devices that we have in the market. But this actually has cost impact with high investments that need to be channeled for this type of technology, and also the high wafer cost that is being compromised by the low yields that are there for new technologies. And also it is very important for the manufacturer to constantly improve their yield and control their yield, eventually to have a cost reduction of this type of technology chip. So this is all that I had for you for today. I will leave the floor for Faika. Thank you so
Thank,
much.
thank you very much, Belinda, for this very interesting presentation. John, the floor is yours.
Thank you, Belinda. Thank you, Faisal. Yeah, so Belinda touched on the cost estimation for the M1, where the blend of 5 nanometer FinFET and the die size bring significant cost implications. In fact, I think we could say that the M1 is Apple's most costly processor that they've designed thus far. Um, what what is interesting, though, is that when we think about we actually see this as a cost advantage for Apple relative to the previous processors they were placing in MacBooks, being an Intel CPU. As an in-house designed silicon, you no longer are paying, Apple is no longer paying Intel margin, but yes, they have to pay TSMC margin, which is maybe similar now to Apple or to Intel margin. However, on a front-end manufacturing cost basis, not the fully packaged product basis. So from that standpoint, we see this as a bill of materials cost improvement for Apple. Not to mention the latest announcement from Apple, I think in the last weeks, was that the M1 would also move into iMac and MacBook Pro lines, which have historically had discrete graphics card placements or discrete GPU placements, and will now go forward with just the M1, which is not only is the M1 displacing prior CPU technology, but also displacing these discrete GPUs going forward. So that carries even more bill of material cost savings implications. And this adds another layer to Apple's vote of confidence in their design prowess, and of course that of their IP partners, namely in ARM. Previously, where ARM-based processors were found in laptops or PCs in general, these were systems where mobility and battery life was valued over the general compute performance capabilities of the processor. With the M1, it seems Apple is making the claim that it's no longer an either-or proposition. So we may see more PC OEMs look to move ARM-based solutions into higher performing tiers, given this release from Apple. And speaking of ARM, NVIDIA announced their new ARM-based server CPU Grace at GTC. So too early to tell what extent of x86 market share, server market share, that would displace, but the value proposition is certainly real for servers already using a GPU for acceleration. It follows it's logically sound to follow that NVIDIA, who has been key on accelerating AI workloads, could design a processor that works complementary with the general purpose GPU. So setting aside the growth in ARM-based PC processors, thanks to Apple, the GPU accelerated server is the fastest growing segment we see in the compute space. So even a small foothold there should make good business sense for NVIDIA and ARM. So taking a moment on the application processor space, the consumer-based application processor market saw revenue for chip designers of $37 billion in 2020. We expect that to grow above $40 billion in 2021 and may reach above $60 billion by 2026. This growth comes from both increasing units in segments like the APU-based laptops, as well as increasing in processor pricing. As Belinda mentioned, the increasing in pricing would reflect the APU's existence in the leading edge of foundry process nodes, and these leading edge nodes are becoming more and more complex to produce at shrinking lithography, and that's going to be an increase in wafer costs from foundries. And designers will likely pass that cost on to their customers rather than eat that cost within their own margin. So in this space, Apple is about 20% of the smartphone market and about 40% of tablets, which in fact is another model. The iPad Pro is getting an upgrade to the M1 coming soon. So it's not only displacing Intel CPUs in the prior MacBook models, but it's also displacing prior Apple A chips or AX chips or AZ chips. And how does the APU-based laptop processor compare to the rest of the traditional compute market? So it's certainly small. The APU piece of this is the darkest blue with the CAGR of 28%. It's less than 5% of total units today in this CPU and GPU view. But as you can see, it's growing at the fastest clip, mainly on the back of this strategic decision from Apple. We have it reaching almost 10% of units by 2026. And I mentioned the growth in these computing spaces. Here we see the revenue picture of the main pillars of compute altogether: APU, CPU, and GPU. In Yole's forecasted revenues out through 2026. Here, I would want to point out the outliers in that growth, of course: server GPU and the ARM-based PC CPU. You have some other strong growth, certainly, in with server CPUs, and there's interesting things in application processors. But to focus our discussion, you can really see how placing the M1 and its successors in our model has swung the APU-based PCs from a lower-end mobility-focused notebooks into capturing a significant portion of that mainstream high-performing systems. And then another way to look at the revenue picture is if we taking a moment to talk about that server side I mentioned at the beginning. Another place to find big growth is looking historically as well as looking forward in the server segment. So here we isolate the server CPU and GPU, put them together, and you see why NVIDIA would be looking to capture more of this space with their Grace announcement. So their leadership in the data centers GPU space, but looking to crack into the CPU space as well. As a whole, we see this segment potentially doubling the combined CPU and GPU placement in server. We see this revenue potentially doubling by the end of 2026. And then as a whole, at Yole, we take a holistic approach to the market model, and given our expertise in the technology side, we can translate our thoughts on end system placements and design wins and die size and process nodes, and translate those back into real wafer volumes in the fabs. And this, coupling that, I mentioned the reason we expect APU prices to climb, and you can hold that in your mind and look at this picture and understand how we think about the future complexity of semiconductor processes. As we see what's a modest increase in wafers here, coupled with what you saw previously of growing revenues, really it's that a wafer ran in 2024 is going to be much more expensive than a wafer ran today, because in 2024 it'll be on 3 nanometer or a mixture of 3 nanometer and 5 nanometer, or at Intel it'll be on 7 nanometer, but ahead of where they are today. And in 2026 the same will be true. Those wafers will be even more complex and more the processes on those wafers will be more complex. So that's really what's going on. And really, so if process costs are going up and foundries want to maintain their margin, and then designers want to maintain their margin, who's really winning in this whole value chain? And I mean, one perspective is certainly that the equipment suppliers are should win. A more complex process requires more equipment to run the wafers. So as you see, this is, and here we're isolating key foundries and the main IDM, Intel. This is a space that required maybe $30 billion of annual capital expenditure as recently as just 3 or 4 years ago. Looking ahead in this year and then for the next few years to come, this is a space that we think should have close to $60 billion worth of capital expenditure. And that is what will enable the kinds of volumes on 5 nanometer and beyond that Apple needs, that everyone else in the SoC designing space will need, and as well as in the fabless and IDM design space.
Thank you. Thank you very much, John, for your presentation. It's time now for the Q&A session. We received quite a lot of questions today. Let's try to answer them. So first question, maybe for you, John. How is Apple able to manage this processor change? And would other OEMs be capable of a similar move?
So Apple has a few advantages here that's playing in their favor that other OEMs may not be able to replicate, at least not near term. Apple is certainly fully capable of designing their own processors for a long time with all of the iPhone chips and the iPad chips and Apple Watch chips. They have a highly capable team behind all of that. The other advantage for Apple there already is that they have complete control over their hardware and software environment. They don't. There's no other devices out there running in an Apple OS that isn't a piece of Apple hardware. So given that amount of control, they're able to tailor the experience and have much cleaner interplay between the hardware and software. And so the M1, when it was released, also came out with a brand new Apple operating system that was meant to complement that. So that sort of activity would be harder for a Windows-based OEM to enable, even a Windows-based OEM to enable, because even if you're Microsoft, putting out a Surface laptop, the operation system you're running is also running on so many other devices in the ecosystem that you don't have control over, or you don't have clear control over, and that will makes things a lot much more complicated to integrate in between the software and hardware side.
Okay, thank you. Yeah, very clear. Thank you. A question for you, Belinda. From the package X-ray image, it shows some embedded capacitors. How many capacitors are embedded, and how are they placed in relation to the M1 die?
Oh, yes, indeed, there were 6 capacitors. You are right, there were capacitors that are embedded inside the PCB. There were 6 capacitors that are directly under the M1 chip. So you had 2 of the capacitors that were under the big core, and you have 1 capacitor under the GPU, 1 capacitor under the CPU, and another one under the NPU, and the last one was under the logic cells. This is the standard cell. So these are the 6 capacitors that were directly placed in position in relation to the M1 chip.
Okay, 6 capacitors. Thank you.
Yeah.
John, a question for you. How much of the data center CPU market is addressable by NVIDIA Grace and its successors?
Yeah, fair question. So NVIDIA pitched Grace as a processor architecture that would combine or integrate with an NVIDIA GPU or data center GPU. So as if we follow that that paradigm, then the amount of servers that are using GPUs for acceleration or coprocessor acceleration, those are the ones that maybe are the lowest hanging fruit, so to speak, on that. So today that's less than 10% of the overall server space. But going out, that's also the fastest growing and the most interesting from AI workload standpoint and machine learning. And so we could see that percent certainly doubling over the next few years. Whether or not data centers and hyperscalers choose to integrate to that solution versus sticking with an x86 based CPU, that's still yet, I think, as I mentioned, it's still too early to tell. But that's the order of magnitude we're talking about in the server space of right now. It's less than 10%, and it could get to mid-teens or even 20% by 4 or 5 years from now.
Thank you, John. Thank you. Belinda, one question for you. Which other players have processor using 5 nanometer process in the market? Could you comment on their gate pitch?
Okay, very good question. When you talk of the 5 nanometer, that is so hot in the market right now, we're looking at the Apple M1, first of all. So this one was actually manufactured by TSMC. And then we also have Samsung that has come in 2020 with their manufacturing. Samsung, there is Qualcomm Snapdragon 888 that is actually manufactured by Samsung. And also Samsung has their own 5 nanometer chip that is out in the market, Equinox 21100. And also we're going to have an analysis, a physical analysis of this and the cost estimation that is going to be coming out later for the reports from System Plus. So what I can actually comment for you on the fin pitch and the gate pitch. Usually for the 5 nanometer that we have looked at, the ones that we have done, we see that we have a gate pitch of about 49 up to 50 nanometers. And also the fin pitch is about 30 nanometers. So this is the estimate that I can give you for this 5 nanometer technology.
Okay, very clear. And maybe another question for you, a last question. How much area on the M1 die is occupied by the standard cell logic?
Okay, yes, I get a lot of that question. On this chip, when we're talking about the M1 chip, as we saw that the chip is actually a system itself, but the bigger part is actually being occupied by the standard cells. These are the logic cells. So on the chip that we actually saw, we estimated about 28% to 30% of the die area was actually occupied by these transistors, the logic cells.
Okay, very clear. Thank you.
Oh,
thank you. The live market briefing is now ending. Sorry, we receive a lot of questions, but we will try to answer by email as soon as we can. So thank you again, Belinda. Thank you, John, for your time and analysis. To everyone, you will soon receive an email with the link to the presentation within 34 hours. Feel free to share the presentation with colleagues. Finally, please let me remind you that you can find all our reports, tracks, and monitors on our website, www.i-micronews.com. Do not hesitate to contact us if you have additional questions. You can find our contact details on the last slide of the presentation. Thank you all for joining us today. Have a good day and take care.
Thank you.
Bye.
Thank you. Bye-bye.
Bye.